The industrial synthesis of sulfuric acid through the contact process involves the catalytic oxidation of sulfur dioxide to give sulfur trioxide. It's an exothermic reversible reaction. You're not expected to know this off by heart. They're supposed to give it to you, but it's really not difficult. You've got sulfur dioxide. It is oxidized, and it becomes sulfur trioxide. It's an exothermic reaction. The following equilibrium concentrations are measured. Calculate Kc. They've given you the concentration, so you don't need a rice table. You just need to say the concentration of the products raised to the coefficient divided by the concentration of the reactant, also raised to the coefficient, and you're going to substitute in 5 times 10 to the negative 2 squared divided by 3 times 10 to the negative 3 squared, 3,5 times 10 to the negative 3. I literally just got those numbers up from here. I mean, they were right there given to me already, and I find that I get 79,365. Use Le Chatelier's principle to explain what happens when the temperature of the equilibrium is increased. If I increase temperature, I always favor the endothermic reaction. Oh, this is getting to be a bit of a fat pen. Favor the endothermic, and in this case I am therefore favoring the reverse reaction. If I favor the reverse reaction, I decrease the Kc value. Will the Kc value, what happens to the equilibrium? I will favor reverse. Will the Kc value for the forward reaction decrease, increase, or remain the same? Well, since I've got less product, I'm going to decrease my Kc value. And then it says, draw a sketch graph of the rate of the reaction versus time to show the changes in the forward and reverse reactions when the temperature is increased. It's going to end up going faster. So over here we've got the rate of the forward reaction, as it would normally be, is decreasing, whilst the rate of the reverse reaction is increasing until they reach some sort of equilibrium position. When I am going to now increase the temperature, so this is all at the lower temperature, I am going to have a much steeper gradient to that graph, but also my rate where the two are going to become even is going to land up being much sooner and much higher. It's going to, both the forward and the reverse reactions are going to be higher. So that would be reverse and that would be forward. Hydrogen and oxygen are enclosed together in a 200 centimeter cubed container. Over the course of time, you've got that. The reaction is started and they give me some information and they want me to calculate Kc. So I'm going to try and do a rice table here. And we've got a volume and we've got a concentration. My ratios are 2 is to 1 is to 2. Initially I put 0,5 moles of both the reactants in, and then they tell me that the equilibrium mixture shows that there's a mass of oxygen of 9,6. So I'm going to take a look at that mass of oxygen and get number of moles. Number of moles is mass over molar mass, which is going to be equal to 9,6, and it's oxygen, so it's going to be 32, and I land up with an equilibrium amount over here of 0,3. So that's 0,3. I therefore need to say how much did I use. I started with 0,5, I ended with 0,3. I must have used 0,2. There's a link between the number of moles consumed and the number of moles of product at equilibrium. So let's just take a look at that. It's going to be 2 is to 1 is to 2, as 0.4 is to 0.2 is to 0.4. So I'm going to just put in my 0,4s over here. My container size is 0,2. Pop that in. I subtract over here 0,5, what I started with, minus what I used, and I get 0,1. And I then divide through, and I get 0,5. Remember, it's number of moles divided by volume, and therefore I get 0,5, 1,5, and 2. Substitute it in. Remember to write the expression for Kc, because even if you get nothing else, you'll at least get that mark. and we're going to say 2 squared divided by 0,5 squared, and 1,5, and I get 10,67. How would a decrease in temperature affect Kc? Well, this is an exothermic reaction, so if I decrease temp, I will always favor the exo, and in this case the exo is the forward, and therefore I will increase the Kc value. This reaction over here is not in the curriculum because it's going to land up involving x's, and so, but we'll go through it just for the mental exercise. I'm going to go through it quite fast. So we've got a rice table again, and we are going to say if I put 0,1 moles of hydrogen and 0,1 moles of iodine, my ratio is 1:1:2, into a 0,5, because it's 500 centimeters cubed, so I divide by 1,000 in order to get 0,5 decimeters cubed. And I am going to then say those are linked, and I get x, x, and 2x. This is 0,1 minus x, 0,1 minus x, and they are going to give me a little bit more information. Well, let's see what they ask me. I've been given Kc over here, so I can say that's my concentration, that's my concentration, and that's my concentration. Kc is equal to concentration of the products divided by the concentration of the reactants. And Kc is 49, and then I substitute in my values here 4x. Don't forget to square the whole thing, divided by 0,1 minus x over 0,5, and as you can see that's duplicated here, so we can say that that's squared, that times that, the first times the second, and I land up square rooting again in both cases, and I'm left with 7 is equal to 4x divided by 0,1 minus x over 0,5, which if I times it, I'm going to invert that, and eventually my x is going to turn out to be 0,08. They ask what is the influence of increasing the pressure. Turns out I've got 2 gas moles on the left and 2 gas moles on the right, so it's going to make no difference to increase the pressure at all. And it says you need to calculate the equilibrium concentrations of the hydrogen gas, iodine, and hydrogen iodide. I take this x value over here, substitute it up into each of those, and I find that I get 0,04, 0,04, and 0,31.